Hi there. So this video is about span tree 802.1d. This is part 2. In this video, let's focus on how the port row selections, the process of how a switch select a root port, a designated port, or an alternate port. So what you're looking at here is a lab that by default has span tree 802.1d, Cisco version of it. It's running, and this is showing the default of all the root port and the port rows of each interface. So I have moved the root bridge back to switch 1, and then switch 2 is the secondary root bridge. And this is the default operation. Let's go through the configurations and look at the CUI output to see why a switch decided to elect or to select the port row for its interfaces. Okay, so on switch 1, we do show span tree VLAN 1. So switch 1 is the root bridge, and the reason is that it has the lowest priority bridge ID. And for the switch that is root, all of its interfaces have a designated row and in forwarding state. The cost is the link, is basically the speed of the link. This one assume that this link here is 10 megabit per second. Okay. So we go to switch 2. We do show span tree VLAN 1. Switch 2 has one of its interface is a root port row, and root port is always in forwarding state, and the cost is also 100. Then it has multiple interfaces that in the designated state designated row in forwarding state. Okay. And we're going to look at the reason why the switch selected this particular interface as a root row, port row, right, versus others interfaces here. Okay. So let's look at 3. Again, it's selected E01 as a root, and then it also have designated row and then alternate row. So we're gonna go over the criteria selections of a port row, right? Whether it's root, designate, or alternate. It's all about the selections process. Okay. We do 4. All right. Again, 4 has one interface has root row. Also have alternate and designate. Go to 5. 5 again has one interface dedicated to be a root port row, designate, and alternate. Okay, so you can see the patterns, right? The pattern is that for a switch that won the root bridge elections, that it is the root bridge, right? We're looking at switch 1 here. It doesn't need to have the root port, right? If it is the root for all VLANs, then every interface will be a designated interface on that root switch. The rest, that is the rest of switch that is not the root bridge, it will have one interface dedicated to be a root port, right? And so we're going to look at that process, that root port selection process, okay? To understand that, let's take a look at this. So these 1, 2, 3, 4 criteria are the selection processes of how a switch decide which of its interface will be the root port. Okay, so this is in the numerical order. So a switch will go through 1 to compare, 2 to compare, 3 to compare, 4 to compare, right? Until it finds something that it could definitely say that the interface is the root interface. Okay. All right, so let's take a look at number 1 first, the lowest root path cost. As you can see, I have the cost of a link, 100, right? The 100 came from the speed of that link, which is 10 megabit per second, and you have 100 megabits a second, which is 19. 1 gigabit is 4, and then 10 gigabit is 2. This value, this cost value, will help determine the root path cost, right? The lowest will win. Whichever interface has the lowest path cost to the root bridge will be selected as the root port. So take a look at our topology here. All right, so if I look at switch 2, you can see E00 has a cost of 100 to get to the root bridge, which is switch 1. And if switch 2 uses E02, it will have a cost of 200, right? It will go through here, which is 100, added another 100 from here to here. So that's higher than this E00. E03, it's even higher. It'll be 300. So just based on the cost, that's the first thing that it's gonna look at, right? For a switch to determine the root port role, it will use a cost, the lowest cost. So the reason switch 2 picked E00 as a root port is because of the cost, lowest cost. Okay. Same thing with switch 3, right? The cost of E0/1 will be lowest to get to the root bridge. So E01 will be the root port. Okay. Now, switch 4 will be a little bit different here because the cost is the same both direction, E03 and 10, right? All 200 to get to root bridge. You add 100 here, 100 here, right? If you go this way, it's 100 here and 100 here. So when the path cost to the root is equal, it's going to use the second tiebreaker. The lowest neighbors, keyword is neighbors, bridge ID. For switch 4, it has to use a different tiebreaker than the path cost, right? So it uses the neighbor bridge ID, the lower one the interface that connected to the lower bridge ID of the neighbor switch will win. So if you look at switch 2 bridge ID, so switch 2 bridge ID is 28673. That is the neighbors of switch 4 going through using E03 interface. Switch 3, it has a bridge priority of 3276, which is higher than switch 2, right? And switch 4 use E10 to go to switch 3 as the neighbors. So between switch 2 and 3, that's are the neighbor of switch 4. Switch 4 would prefer to go through switch 2 to get to the root bridge. Therefore, it elected E03 as the root port because its neighbors, which is switch 2, has the lower bridge priority versus 3. Okay? So that tiebreaker using lowest neighbor bridge ID in this case scenario for switch 4. All right. So what about switch 5? So switch 5 also have the cost equal between the two links, E01 and E00. That's trying to get to the root bridge, right? So it'd be 300 either way, right? So that tiebreaker of the path cost is not going to work for switch 5. What about lower neighbor bridge ID? Well, switch 5 only connected to switch 4, which is the only neighbors, right? And switch 4 has basically the same bridge ID priority from switch 5 perspective, which means the criteria or the tiebreaker for 1 and 2 doesn't work here for switch 5. So then it's going to use the next tiebreaker priority. So it's going to look at the lowest neighbor port priority, right? So the neighbor of switch 5 is 4. So look at the switch 4. So from switch 5 perspective, if it uses E00 connected to the neighbor E1-2, what is the priority of this interface? E12. Right? If we look at the output on 4, what we care about is the neighbors, right? Port from whatever that switch we try to determine, right? So E12, the priority is 2835, right? And if switch 5 uses E01 to get to switch 4 neighbors, and that's connected to switch 4 E1011, so the priority is 128.34, which is lower, right? Which is lower than this guy. So what do we have here? So you can see, right, switch 5 decided, yeah, that this interface is blocked or designated port in this interface as designate, right? The reason, right, is because it sees that the neighbor's switch interface, which is E1, that's one, has the lower priority, right, interface priority, than this guy, E1, 2. So from switch my point of view, it sees that the neighbor interface has the lower priority than if it will use a different interface to get to that neighbor, right? So that's what the lowest neighbor's port priorities use case is, right? So that's and if they happen to be the same, right, and then it will determine the neighbor port interface number as well, right? So this specify uses the scenario, the tiebreaker number 3. Okay, and that is, I'm sorry, let me correct this real quick. Again, it needs, every switch that's not a root will need a dedicated interface as a root, okay? All right, so this is correct. Okay, so that is how the root port selections happens by default. Again, if you want to manually kind of configure the interface to be a root interface, then you could do that with, you know, just based on the selections you could modify. But we'll talk about that in the next, maybe another video. All right, so that's root port selection. All right, let's talk about the designated port selections. So the process is, again, kind of similar to the root port, right? You have 3 criteria here in order. That's how the switch is going to look at, right, from 1, 2, and 3. And the path cost, again, will be the first criteria the switch will look at to determine. And then the lowest local bridge ID. The keyword here is local versus the root port selections usually is the neighbor's bridge ID that it looks at. So, and then the designated port will look at the local port ID. All right, so let's look at our topology here and see how these 3 criteria apply to the selection process. All right, so what's interesting here is that, let me move this back. All right, what's interesting here is that we want to see the designated port links between switch 2 and 3 here, this link right here, right? Now the question is, why is switch 2 EO2 is designated port versus switch 3 EO2 is an alternate port? So why is that? All right, so if we look at the criteria, so the 2 switches is going to use the first lower priority, the first criteria, which is the path cost. Lower path cost wins, right? And so if you look at this one, the cost is equal right? Whether the switch 2 uses this link or switch 3 uses this link, right? Its own link. So 200 is equal. So then the path cost doesn't apply here. So the two switches, going to move to the second criteria here, which is the local bridge ID. And again, the keyword is local, right? Local, which means is the switch will look at its own bridge ID to see who's the winner, right? We'll just do show spanning tree one here. All right, you can see that this local bridge ID, switch 2, is 28673. And then versus switch 3, we do show spanning tree using VLAN 1, an example. Local bridge ID of switch 3 is 32769. So between the two switches, 2 and 3, 2 has lower bridge ID, which means its interface will always win the designate port selections, right? And the losers, which is 3 in this case, will have to make its interface as alternator, right? So that is the selection process of designated port and alternator port between the switches, right? The links that connect between those switches. Same thing over here, right? So you have switch 4 versus switch 3. Okay. Now, in this case, right, it's very clear that switch 3 is going to win because just based on cost from itself, right? From the local switch itself to get to switch 1, the cost is only 100. But switch 4, right, to get to all its interfaces, right? We don't have to count this interface, just all interface, right? The lowest interface getting to root bridge on switch 3 is this guy, which is only cost 100 to get there. But switch 4 will be at least 200, right? This cost out of this cost to get here. So from just the path cost perspective here, right, switch 3 is going to win that designated port. And the losers will have to be an alternate, right? So switch 4 will put this one as alternate. Right, again, the root port already been selected, right? So it's just between the designated port and alternate port, right? All right, so that is taking care of why this link on switch 4 is alternate port. On switch 5, all right, let's take a look at switch 5. It has an alternated port and then a designated port on switch 4, right? So why does switch 5 lost this link to switch 4, right? And obviously, it's the same thing. The cost will be a problem in this case as well, right? So the cost from switch 4 to get to root bridge is 200, right? Lowest. But switch 5 will be 300. So again, the cost, right, will win for this case as well, right? For switch 4 will be designated port here, and then switch 5 will have to turn this port into the alternate port. Now, the key point of alternate port is that it's going to be applied on the redundant links, right? Anything that's redundant, right? So, and that's the whole goal of spanning tree, is to make sure redundant links are put into a port rows that won't cause the spanning tree loops issues, right? So that's the whole operation of spanning tree, right? So next video, I think we're gonna play around with the menu configurations, like how would you influence the root port, or how would you influence the alternative port, right? So you can move it around. That's just in a way to design your spanning tree network if you need to, right? But by default, right, this is everything default. Beside, I may switch 2 as a root bridge and switch 2 as secondary root bridge. But every port role is by default within the spanner tree operations automatically configure itself. All right. So that's it for this video. So hope to catch you on part 3 of spanner tree 802.1d.